Hi, today is a continuation of the previous video where we modeled it's a DC motor. We used the DC motor to drive our gear system. Then using the sensor subsystem, we can measure the speeds, the input and output speeds from the gear system. Okay. For a system to be solved accurately, it needs initial states and initial conditions, because the solver usually determines all initial conditions of all states in a physical network. Okay, if there's a contradiction of initial states or the initial values not being consistency, the system brings out an error. Let's do this practically. We have a gearbox that is supposed to be in motion. Let's assume that the gearbox has some rotational motion that indicated by the inertia. Remember, this inertia displays the motion of the represents the motion of the gear system inertia. Okay, if you double click the inertia block, we are using the parameters. We are using the default value of 0.01. For the variable section, we usually have this where you set your initial values and initial condition. We're going to use a rotational velocity. We're going to assume that the initial value of the gear system is 10 radians per second. Okay, then we have three types of priority: high, low, and none. When you select none, this initial value is ignored by the system. When you select high, it is given high priority. If you have another system with a low priority, the solver gives high variables first priority. Therefore, in this case, let me use 10, apply. Then at the same time, let's assume our DC motor has some initial value of initial rotor speed. I'm assuming the rotor speed will have some initial motion. Let's use 10. We're going to use 10 in both scenarios, radians per second. Okay, I'm using initial value of 10 in the inertia here. 10. I'm using a value of 10, variable 10 rad per second. At the same time, 10 mechanical initial rotor speed of 10. Okay, let's now you go to debug, you select Simskip, you use a variable. You want to view the variables, variable viewer, maximize here, you can collapse, then you refresh, wait some few seconds. It's already refreshed. You can collapse again. You can see we have unable to certify all high priority targets. Why? Let's see the reason why we have this error. Remember, we gave a DC motor value of angular velocity of 10. That was our target value, initial value. At the same time, our gearbox for the inertia, we gave it 10. That was the target value of 10. But you see both priorities are high. Okay, and remember the gearbox, the ratio is 2. Meaning, if this is 10, this can never be 10. They contradict because the gear ratio is supposed to be 2. As you can see here, it determines the appropriate values and assigns the DC motor value of 12 rad per second and assigns the inertia 6 rad per second. You can see the gear ratio here is 12 divided by 6, it is a 2 from our. If you go back to the gear ratio here, this 2. Okay, you can go back to variable viewer. Here it is. How can you now solve this? We have to give one of them high priority and one of them low priority because they now contradict. Therefore, right click on W for the angular velocity, open block dialog, and I'm going to use variables here. The variable for the inertia, instead of high, low. For now, a low. Okay. Then you refresh variables again. You collapse. You can see now you have just one error, that is in gear system, because all high priority targets certified, bottom corner, but some low priority targets not certified. Why? If you go back to the inertia, even if you give a priority low, but the value of 10 contradicts the gear ratio. That's the reason why. If you go back to DC motor, this 10, the error disappears because 10 is high priority. Therefore, the target and the start gets the same value. But if you go to the inertia, low priority, this is 10, this is 5 because of the gear ratio. Therefore, this one can never be certified. Let's go back to dialog. Let's go to use none. Okay, refresh. Refresh, collapse. Now there's no error that appears because now we have given the DC motor the initial value, but the gear system we have said do not consider that 10. It disappears. You can see because we have selected none. That's how you troubleshoot the initial values. We are going to, as we advanced into a deeper complex models, you're going to see the advantage of that. Okay. Lastly, you can see I'm using the scope to get the value. Instead of using scope, I can also log. You can log this data so that you can be able to view. How can you log the data? You go to modeling. You go to model settings here. Model setting. I'm using a Simscape. For the data logging, I want to log all data. Then open viewer after simulation. Therefore, the data will be saved in a workspace variable called simlog. Then I can be able to view the data. The data contains input speed, output speed, all the parameters in my system, all the variables, okay? Therefore, you select open viewer after simulation. Then this one limits the data points. Do not limit. Get everything. Then apply. Okay. If I go back to simulation, if I run, it opens for me the data viewer. From here, I can open, for example, can open gear subsystem, gearbox. For the gearbox, I can get the value of input shaft from there. This is the value of output. Let me get this gearbox here. This S is the input, this O is the output. Therefore, we need the value of this O. Let's do the comparison with the scope. You can see the input is around 55, output is around 27. Let's see the from the viewer. Let's see. You can see here output is around 27, the same value. Input around 55. If you select the line, you can see the value popping out. Therefore, 55 rads per second. Therefore, you can get all the parameters you need from here. Meaning, you don't need a sensor subsystem. You can eliminate this one and log your data. Okay. Thank you for your time. In my next video, I'm going to now to start a series whereby we are going to discuss the types of motors used in electric vehicle and see how we can now integrate them with the mechanical system. Progressively, we are going to make the EV. Therefore, stay tuned. See you in my next video.